PhD and master's in 2005 and 2001 from the University of Washington. Her PhD thesis focuses on designing a generative model for human natural motion. She was an assistant professor at the University of Southern California starting from January 2006, and she was there until she joined Georgia Tech in August 2007 in the School of Interactive Computing. She has received the ACM SIGGRAPH Significant New Researcher Award, and she has also won the Open Source Software World Challenge for her work on DART, the Dynamic Animation and Robotics Toolkit. Her research interests are in computer graphics and animation, including physics-based animation, character animation, optimal control, numerical methods, robotics, and computational biomechanics. She has also done some very cool recent work on robotic-assisted dressing and cloth manipulation, as well as some very inspiring prior work on character animation for dexterous manipulation, bicycle stunts, and other tasks. I also want to add that immediately following her talk, everyone will get a chance to talk further with Karen at the post-seminar reception at 4:30 in Newell Simon 1507. Let's all welcome Karen.
Thank you. Thank you. Can people hear my voice in the back? Yes? All right, thanks. So it's definitely my great pleasure to come here to give a talk at the RI seminar. So today I'm going to mostly talk about the work that we did in computer animation and its potential implication in robotics. So one of the grand visions in computer animation is to create virtual humans that can move realistically. So we want this, just like in the real world, we want this virtual humans to be able to navigate the environment, to manipulate objects with different properties, and to interact with each other intelligently. So this means that behind the scene, we need to be able to simulate the physical interaction, to model the perception, and to in the decision making as well, to create this truly autonomous and believable virtual humans. So we have seen many lifelike, beautiful character animation from computer animation. And a lot of those animation you've seen are created for entertainment applications. And perhaps because these entertainment applications can be computed and rendered offline, there hasn't been this urgent need to push this the advancement of autonomous virtual humans. And interestingly, some recent development in robotics actually motivated a lot of researchers in computer animation to revisit this vision of creating autonomous virtual humans. So we start to see a lot of this sort of emergent research areas at the intersection of computer animations, robotics, and artificial intelligence. And this change, I think, can be traced back to these two distinctive events in robotics in the last 5 years. The first one I want to highlight is this DARPA robotic challenges. I think many of you probably participated in that. So the goal of the DRC is to really promote this premise of humanoids, right? We want humanoids to move like humans, such that they can adapt it in the man-made world. And the second event, I think it has a great impact, is the NSF National Robotics Initiatives. So the whole concept of a co-robot, right? Putting robot together with humans in this collaborative setting. And that really makes the require research to rethink robotics from the perspective of humans. So these two top-down efforts from the national funding agency actually have some unintentional impact in computer animations, because they basically highlight two, I would say, the most important problems that we're trying to solve in computer animations: how to move like humans and how to interact with humans. So today I'm going to mostly talk about the second question, how to interact with humans, but I will also mention just one project about how to move like humans. So how to move like humans. This is one of the most important research problems that computer animation researchers have been investigating for decades. Physically based character animation has evolved to a point where we can simulate complex human motions with great visual realism. So if you're just talking about simulation, we're actually quite confident that we can get a virtual agent to move like human to some extent. But apparently this is not good enough. If we can only do things in simulation, we can whatever, however we make the virtual agent move like humans, it's not going to make any impacts in robotics. So here's a quick example. We learn a control policy in simulation, and as soon as we apply this to the real world, you can see that it just doesn't work. And this discrepancy between what can be achieved in simulation and what can be achieved in the real world is referred as reality gap. And the reason to reality gap, well, there are many reasons to that. For example, dynamics model discrepancy, the lack of uncertainty in our simulation, the limiting of the sensing capability in the real world. And beyond that, there's a lot of unmodeled factors. So to me, we really need to, if we ever want this work we did in computer animation to be transferred to robotics, we really have to tackle on this problem to close this reality gap. So today I'm going to focus on one particular aspect of a reality gap, dynamic model discrepancy. So, model parameters. It's a set of parameters that define the dynamic model of a system. For example, the initial parameters can include the location of the center of mass. The joint parameters can include joint friction, joint damping, stiffness, and contact parameters, for example, can include the friction coefficients. So suppose this is a space of all the model parameters we consider. Every single point in this space is a vector of model parameters that define a dynamic model. If we can pick the current setting, the default setting of your physics engine and your robots, and train a control policy for that. But the real world, the parameters in the real world is likely to be different. So if we directly transfer the control policy we train for this green star to this red star, it's likely to fail. And people usually mitigate this problem in two different ways. One possible approach is to train a more robust controller such that it can handle a reasonable amount of noise based on the hypothesized dynamic model. But the drawback of this method is that it will only work if your hypothesized dynamic model is close enough to the real world. Alternatively, we can try to train a dynamic model using the real world data by iterating between control policy training, data collection, and also dynamic model fitting. The drawback of this approach, however, is that sometimes it requires a large amount of real-world trials, which could be expensive, could be time-consuming, and dangerous to acquire. So our approach to model the discrepancy between model parameters is slightly different. Assume that we can learn a control policy for every single point in this space, meaning that for every single dynamic model, we learn a control policy for that offline. Suppose further that during online execution, we have a very fast method that can tell us which dynamic model best fits the current sequence of observation. Okay? So with these two hypothetical models working together, during online execution, all we need to do is to look at the recent history of our state and action pairs, and then select one dynamic model that best fits that, best explain what we observed, and then execute this control policy corresponding to that dynamic model. Of course, this is hypothetical. In reality, there's no way we can pre-explore or pre-learn a control policy for every single dynamic model in the world, but it might be possible to learn to pre-learn a continuous parameterized space that covers a subset of states that we care about for this particular task. So with that idea, we designed a an algorithm that based on reinforcement learning. So this is your standard setting for reinforcement learning. You're trying to learn a control policy that take as input a state and maps to an action such that the expected return is optimized. If it's in a simulation setting, then this action will be fed into the simulator, which will be used to produce the next state through the numerical simulation. So our algorithm, however, deviates from the standard setting a little bit. Instead of just inputting the current state, we also take as input the model parameters. And these model parameters could be, for example, the torso, the inertial property of the torsos of your robots. And we call this universal policy because this policy can produce an optimal actions for a parameterized space of model parameters. And the problem here is that in order to use this universal policy, we need someone to provide the value of this mu, of this model parameters, at every single time steps. To solve the problem, we train a separate neural networks which predicts the model parameter mu based on the current state and a sequence of previous actions and states. Basically, a short, a recent history of our observation. And we call this online system identification. Okay? So during online execution, every single time steps, we're going to query this online system identification. What is the best, which dynamic model I'm using right now? And together with the current state, this universal policy will produce the best action. Okay? And one thing that worth noting is that this online system identification can be trained using supervised learning, which is a lot easier than reinforcement learning in general. So a lot of people ask this question: why don't you just train an end-to-end reinforcement learning problem? You could just have a recent history as your input, and then directly output the best action. So I think that might work. I think with enough rollouts, you can even use LSTM to make it work. But I think there's some advantage about decoupling this problem into two parts, because we can offload a big part of a learning into supervised learning, which makes everything a lot easier. And we can do supervised learning because we train everything in simulation, where we can provide unlimited number of training data with labels. So that was the rationale that we want to decouple problem this way. So here's some quick example. We show this algorithm working for a number of examples, and here's one of them. We train a single-legged hopping robot, and one single control policy can handle a variety of friction coefficients of the surface. So, and the important thing is that the friction coefficient is not given to the robots, not given to the control policy. It's identified during online execution. And we demonstrate that this algorithm can also work in the case where you have this changing environment. This track has friction coefficient 0.9, except for this blue patch here is more slippery. And we can see that the robot is able to hop across that without falling. And again, the friction information, the friction coefficient information is not given to robot. It's identified by looking at the history of the performance. And here we plotted the identified friction coefficients in red, comparing this with the ground truth in green. All right, so that's all I want to say about the first topic. I have another project I was going to talk about, but then I realized it would take another hour to cover everything. So let's quickly move on to the second problem: how to interact with humans. One challenging scenario of co-robots involves physical interaction between the robots and the humans, like this video you're looking at. So this is really encouraging to computer animation, because now we believe the robot needs to understand and predict the behavior of humans in order to provide the best assistance to humans. So today I'm going to focus on a particular type of a robot assistance. How do we teach robot to put clothes on human? Here are some facts about assistive dressing. So dressing is one of the ADLs, the activities of a daily living, which are everyday tasks identified by health care community as important for independent living. And dressing among all the ADLs is the one that's frequently requested by older adults. And caregivers spend, whether at homes or in the hospital, spend insanely amount of time on this particular task, dressing. So we believe that robotic assistance with dressing has the potential to augment the capability of older adults and improve the life quality for not just care receivers but also caregivers. But dressing is actually a very difficult task, mainly because it's highly collaborative and interactive. So in order to succeed the task, the human has to actively participate in this task. Sorry. So how do we tackle such a problem with so many moving parts? We know that we have a robot, we have a human, and we have a piece of garments in the middle. How do they actually relate to each other? We know that the robots and the humans have sensing capabilities and control capabilities. So we know, the sensors will produce some kind of observation, and the controller will take the observation and produce an action. So that part we know. We also know that sensors should have ability to partially sense their own states and maybe each other's states, as well as the state of the environment. In this case, will be the garments. And in addition, the state of the robots and state of the humans can also affect the state of the cloth through dynamics, through physics. So yeah, that's how they look like, their relationship. And in order to formalize this problem, we need to think about in terms of control. And to me, the first thing that comes to mind is to formulate this problem as joint optimizations. Here we have two dynamic systems, robots and humans, and they are trying to collaborate to achieve a common goal, which is described by my objective function J. And they need to follow the physics, right, laws of physics, which is described by my joint ODE, the differential equations. So to be more specific, Kx here, let X be the joint state space of the robots and humans, let U be the robot controllers, and let V be the human controllers. Okay, so that's my problem setting. In order to directly solving this problem is really difficult because it's a joint optimization. It's a high dimension of both in terms of the state and control. So we can reformulate this problem a little bit by introducing this function G. And G is a function that returns the solution of the optimization over V only for a particular initial state and a particular robot control. Okay, so if you just like merge these lines together, this reformulation didn't make any changes from the initial joint optimization. The only thing difference in here is that now I can separate this, I can decouple this robot control problem from the human control problem. Okay, and if you now look at the right hand side of this equation, and you put X and U together into one vector and call it your state vector, and you look at the V and call it your action vectors. This part right here could be formulated as a reinforcement learning problem, right? I have my J, my objective function, which is a long-term expected return, and then I have my equation of motion. So that means we can use a model-free method to solve a control policy for the human, for the variable V here. And this whole thing can be decoupled into two steps. The first step is to solve an optimal human policy, which take as input the joint state space X and the robot control U, and produces an action, human action V. We can use a lot of recently developed policy learning algorithms in deep reinforcement learning communities, such as TRPO, PPO, or actor-critic method type of the family method, actor-critic family methods to solve this problem. The reason I mention those methods is because those methods not just give us a control policy, it simultaneously approximate a value function. Okay? And if you look at this value function, what does it return? What is the output? It outputs the expected return from the current state following the control policy. So if this control policy at the end is optimal, then what this value function outputs will be G, the solution of G. And that's a good news because now my second step, when I try to optimize the robot control, it becomes super easy because all I need to do is to optimize this value function V over U. And oftentimes this V is represented as a neural network, which means that the gradient is readily available. And I can use any gradient method that I like, the gradient-based method I like to solve my robot control. So this is nice, but the catch here is that this step number one is super hard to solve. If I want to find a policy that's optimal everywhere in this state space, it's equivalent to solving the original problem, the joint optimization problem. It's not any easier. The good news though is that now I formulate this way a model-free problem. This means that I can partially solve this control policy only for the state space, the subset of the states that I care about for this problem. So there's a hope to solve this problem if we are okay with a partial solution. The problem I see is more fundamental is the following. This original joint optimization problems is not very realistic in the sense that it assumes that the robots and human can have this kind of mutual can see each other's states, right? They're mutually observable, I guess that's the word. And they can discover each other's full states. So that is usually not true in reality. And another thing this problem assumes is that the robot controls and the human controls are centrally coordinated. It's like one system, and then they can figure out what each other is trying to do and then coordinate with each other. And that is also not reality. And this can be seen by the fact that this human control policy we try to learn actually take as input the control of the robot. Yeah. So that basically means that this policy knows too much. And what we need to do is cut out some channels of this input space and define a more realistic input space for that. And exactly what this input space should be, that really depends on the task and scenario, which I will talk about more in details later. But anyway, this is sort of framework we want to apply to all our algorithms developed here. But the first task for us is to develop this human controller, human policy. And very quickly, we decided that we can't really learn this human policy from the real world because all those policy learning algorithms demand insanely amount of rollouts. And imagine those rollouts all involve physical interaction between the robots and humans. We all know that robots not really good at the beginning. So if you just apply robots, at least especially at the beginning, it's pretty much just choose random action and apply to humans. So we're going to take the approach of a safer approach, which is what we did in computer animation. We're going to replace that with virtual humans in physics simulation. So the traditional approach to human modeling is to design a procedures based on maybe some motion capture data or some assumptions. It works pretty well in computer animation for well-structured motion, like locomotion, for example. But design such a procedure for a loosely defined task, such as being dressed, is likely to be very biased, at least biased towards whatever motion capture data you use. So to see this more clear, the same space, but now it means the space of all robot controllers. So suppose this is all the controls that PR2 can achieve. Given a particular virtual human model, we can find the best robot controller that serves this virtual human. So for example, if this virtual human is just a static mannequin, then we can find the best robot control for a static mannequin. And we can also, if now we have another virtual human, which is based on some motion capture data, we can also find a best controller for that virtual human. And it's likely to be different, right, those robot controllers. So this means, since we can't possibly model, every single human behavior in this space, whatever we do, this robot controller is going to be biased. But one interesting observation is that even though those virtual humans disagree on what the best assistance a robot can provide, when the robot provides a very bad assistance, they are usually in agreement. So this means that instead of modeling what a human typically would do, we should be modeling what human cannot do, right? Because usually, when you talk about so basically this means that our approach is to model the range of a human capability in the context of addressing. And this kind of modeling is less biased towards a particular set of data, and it's also more easily to identify, to quantify mathematically. So I'll show you a few motion sequences that we did in computer graphics. Sorry, back. Can I go back? Yeah. Even though this is just self-dressing, but this project is sort of proof of a concept that we're able to create a controller to manipulate physically simulated garments for self-dressing. And these controllers that we created is model-based, or some might even say a little bit handcrafted. But even with that, we learned a great deal for us to move on to the assistive dressing. Here's the dressing with a different style. Oh, sorry. I don't know why. Does it play? No. Oh, I see. It plays here, but not on my screen. And we also test this with an example to extend this to assistive dressing. But here you can see the assistant behind this, the character is not really doing anything. All it does is really just holding the robe. So even though this is not real assistive dressing, but this is really good starting point for us. Despite some success, the handcrafted self-dressing, however, fails very quickly when we test on the more challenging garment, such as this tight pullover shirt. We hypothesized that the main reason for failure is because in addition to vision and proprioception, haptic modality is also very important for manipulating deformable objects in a constrained space around the human body. Yeah, he's done. It's not like I cut off, he's done. The first problem that we're encountering is that how do we encode all these variety of modalities into our input space? And the second problem here clearly is how do we design the reward function such that we can constantly get the enough learning signals throughout the learning process. So one possible way is to throw everything you can sense into the input space, right? All the raw data that you can get from your sensors, like proprioception could be the joint position, joint velocity. The vision could be, just the pixels that you see from your eyes, and haptic information could be, the pressure applied on the surface of your body. This could also be encoded as another form of images, and the output will be directly joint torques. So while this end-to-end learning scheme is getting more and more popular in the deep reinforcement learning community, we don't think end-to-end can be applied to the dressing problem for the following reasons. The first is that haptic is really hard to figure out. Basically, we ask the agent to utilize haptic information for two opposing tasks, to apply force and to avoid force. And here you see those very fine red lines. Those are the forces that are sufficient to rip the cloth apart. So basically, the agent needs to understand some contact forces need to be avoided. Some contact forces are required in order to complete the task. And the good contact forces and bad contact forces are not necessarily classified by their magnitude. So all this information need to be teased out by our policy. That's the first challenge. The second challenge is pretty much the only instruction you get from dressing is, at the end, you need to be dressed, right? The agent needs to be dressed. And how do you define being dressed itself is a problem. But the bigger problem is how do you define this reward function? Because naively defined as a final state as a reward function is going to be very sparse. You're not going to get a lot of learning signals throughout. So that is the second issue we're facing. The biggest challenge, and perhaps the hardest one to solve, is the fact that class simulation for rollout generation is insanely slow. It basically pushed the training time from days to weeks. It sounds very trivial, but it is not. It dictates everything. It dictates how we design our reward function, how we make decisions, our input space and output space. So yeah, it's definitely a problem right now. So because of that, under this really strict rollout budgets, we need to design a very compact input space, but also informative. And on the other hand, we can't really give this input space too much information that's not attainable by the human perception system. So with that in mind, instead of using like just an image to represent the haptic information, we have very carefully crafted aggregated forces along the arms of the humans. Instead of using CNN, we directly give our input space the important features of a class, like the location of the arm, the opening of your sleeves, or the locations of the armhole. And that is how we mitigate the problem for the input space. The second problem is the design of a reward function. While the input space to the policy needs to be restricted by the human perception system, the input to the reward function can actually take advantage of the simulated world where everything is observable. So we define this very elaborate reward function that measure the progress of dressing. Basically, we're calculating the coverage of the human body by the cloth using all the information we can get, including the state of the garments and state of the human agents. And with that, we can provide this continuous learning signal throughout the entire learning process. And here is some results we got. In this case, we are able to train a human policy capable of addressing an arm under a variety of robot assistants. Here, I'm not showing the robot, but the gripper is is a robot. Is controlled by a robot, and it's moving in an arbitrary linear line towards the human, and the human has to figure out a way to get its arm inside. And here is another example where the gripper is coming from the different directions. So just to show the importance of haptic information, here I demonstrate I plotted the results of a tube control policy. One uses haptic feedback, one doesn't use it. The first row, the top row here, shows the progress. Here you can see that the policy without haptics actually makes progress faster and even achieve better progress at the end. But this comes with the price of deformation in the garments. If you look at the second row, this kind of deformation in garment, you can imagine the garment will be ripped apart already. And here's a visualization for that. On the right hand, the sequence on the right is the one without haptic. And in this example, the arms quickly make progress by puncturing a hole into the shirt. So one thing you probably noticed already is that the poses, this pose of this virtual agent doesn't look very natural sometimes. And this is because the poses, the joint limits we use is very naive. It's really just a box constraints where for each degree of freedom, we define the upper bound and lower bound, and that's it. And that brings back the notion of modeling the capability of a human that I mentioned earlier. And the awareness of the range of a human motion is really important when you're talking about physical interaction between robots and humans. But setting this joint limits sounds easy, but it is not. Not only that each degree of freedom has a different range, this range actually varies based on the position of other joints. So for example, if your arm is in front of your torso, you have a really wide range to flex your elbow. But now if you put your arms behind your torso, that range becomes a lot smaller. So this is something that we learned from biomechanics literature. And luckily, Michael Black and his colleagues in Max Planck recently developed this really comprehensive database of human poses, where they captured a variety of extensive stretching poses from trained athletes. And they also used this database to develop a procedure, they call it a validity procedure, to determine a given human configuration, whether it's valid or not. So the input to this procedure is a human pose, and output is a binary vectors, where each element in this vector indicates whether a particular bone is in the valid position or not. This validity procedure is not an analytical function, which means that in order to evaluate that, you have to go through a lot of discrete operations like if statements and table lookups, etc. And for example, this table right here demonstrates the valid joint configuration. Every single point in this, I guess, occupancy matrix, if you will, shows that whether this configuration is valid or not. And you can see why the box joints wouldn't work. If you look at the boundary, it's extremely complex, and using box constraints is not going to be able to capture that. So this procedure is very useful. How do we use that? Well, one naive way to use this procedure is to put it in your reward function, right? So if you have a pose that's being, and then you can validate that using that procedure to see if it's a true or false, and then penalize that accordingly. But adding any terms into your reward function in general is a bad idea, because the reward function is already very difficult to design, and you don't want to make it even more complicated. So ideally, we want to be able to enforce joint limits through simulation. Just like the contact and the collision should be enforcing the physics engines as a black box. You should never try to penalize a collision in the reward function. So we want to do the similar thing for the joint limits. So if you want to enforce joint limits through physics, we first need to define a constraint function. And we propose to represent the joint limits as an implicit equation. Okay, so this function C take as input the joint configuration. So if this function evaluates this particular joint configuration on the positive side, that means it's valid. Otherwise, it's invalid. Okay, so our goal is to learn that function C. But before I talk about how we learn that, the first thing is, once you have a C, what can you do with this? Every single time instance, we're going to check if the current position, Q, current joint configuration, is valid or not. If it's right at the boundary, that means C of Q equals 0, then that means we need to solve for a constraint force in order to make sure that in the next time step, this C doesn't go to the negative side. This means that we need to satisfy the following three conditions we call complementarity conditions. The first condition is really just C dot, right? C dot has to be the velocity of a constraint, must be non-negative, because if it's negative, that means in the next time step, your C gonna be negative and your joint limits is violated. And the constraint force itself has to be positive as well, because it's a unilateral force. You can only push the joints into the valid region. You can never pull it to the invalid region. And the last condition basically says that if this constraint force should do 0 work if the joint position is moving away from the boundary. So exactly how we solve this is not important. The important thing to see here is that we need a C that's differentiable with respect to Q This means because we need this Jacobian to compute this constraint force. And that means we could learn a C using a neural network. This time it's not reinforcement learning, it's just old school regression. We do a supervised learning and try to learn a C to model the boundary of the joint limits. How do we get the training data? Well, we can use the procedures that Michael Black and his colleagues provided. All we need to do is to randomly sample the joint the joint configuration in the space of the joints, and then you call the function that provided by Michael Black and give us a label. So in this way, we can create unlimited number of training data and train a very accurate the classifier to determine the range of human motion. And with that, we can design a physics engine that specializes in simulating human motion because it respects the range of a human motion in a very accurate way. So here, what you're going to see is the two completely passive characters, meaning that they don't use any of their internal force, and they're just going to fall under gravity. And the one on the right only uses the traditional box constraints, and one on the left uses our data-driven constraints. And without any control, internal control, you can see that joint limits alone can already create some lifelike behaviors. This is no control, it's just joint limits itself. And another example here, this is in the situation there's no gravity in like outer space. You have this virtual astronauts where they are pulled from their left arm at the beginning of the simulation. And this is with a box constraint. And this is a constraint people usually use. And we're not really, trying to make it look bad. We're actually very carefully selecting the upper bound and lower bound for each joint. And this one is with the data-driven constraints. So besides dynamic applications, we can also use this joint limits for inverse kinematics, right? When we solve inverse kinematics, we can guarantee to get a pose that's humanly possible. So in this case, we're trying to get the character to reach an unreachable point in the back. And you can see that with box constraints, you can do that, but with our data-driven constraint, you will just stop at the right place. That's where you hit the boundary of the joint limits. And we also observed that with the joint limit constraint, the data-driven joint limits, we can also mitigate the problem of self-collision, right? This probably happens a lot when you are dealing with modeling humans. If you're trying to do IK to get to that point, well, of course, the best way to get there is just go through your torso. But with the joint limit, with the data-driven joint limits, you actually avoid that penetration without doing any collision detection. This just comes for free. And that's not surprising, right? Because we learned this from a database. And that database is from real humans. And real humans don't, self-penetrating. So then of course we just learned that as part of the invalid region in the space. So I talk a lot about how to model humans, and now let's get back to robots. So how do we design a robot to provide dressing assistance? The first problem we want to address is the sensing capability, robot sensors. So vision is limited due to occlusion of claws on the human body. And there's not much we can do about that, right? Because occluding human body using claws is like, that's the nature of dressing, right? So it's not like we can come up with a more clever algorithm to enhance computer vision. However, there's a lot we can do to enhance the haptic capability of the robots. So essentially, we want to teach robot what a person feels when it applies an action on the human body. Over years and years of experiences and learning, human caregivers has a pretty good expectation on how the person might feel when he or she apply physical force on the human body. But robot doesn't have this kind of common sense unless we explicitly teach the robot how to infer this human haptic perception. So So you might think clothes is harmless. What kind of damage can clothes do to you? But actually, it can apply a very high amount of force and cause discomfort on human body if you are pulling really tight. So we want to be able to capture those pressures applied on human body using a textile image. Because this image is really informative, it can tell us which part of the human body is covered, and it can also tell us whether the cloth is caught and by which part of the body. So one way to get this kind of information is directly measure from the real world using wearable sensors. But this is a kind of impractical, right? Because imagine if you, in order to get dressing assistance from the robot, you first have to put this wearable sensor on yourself first. It's just silly. So wearable sensor is not something that we can do easily. Instead, we want to be able to infer this haptic information from the limited sensors that robot has. So to be more specific, we want to create an estimators, which input is the force and torques information measured at the end effectors. And output will be the haptic perception represented in the form of textile images. Okay, so that's the input and output we want to learn. And we train our model on data generated entirely in the physics-based simulation. This allows us to quickly generate thousands of training data, and without worrying about hurting the humans in the scene. And with that, we can create this training pairs where the input is the trajectory of the force and torques measured at the end effectors, and the output would be the haptic information as images. And with this, again, because everything is generated in a simulation, we can generate as many as we want and train an LSTM to do this kind of haptic estimation. To test our haptic estimator, we command our robots to follow arbitrary trajectories. That's where this green box is. And you can see on the left is the predicted haptic information from our estimator. And on the right is the ground truth that actually being simulated through the physics simulator, the cause simulation. So basically, all robot knows is the three vectors that's shown on the green box. And from there, robot has to hallucinate, what a person might feel on their body. Okay, so how do we take advantage of this inferred haptic information in decision making? One straightforward way is to evaluate the candidate's action using this haptic estimator. But successful dressing also required a policy to consider future impact caused by this candidate action instead of just the immediate next stage. So we wanted to, one approach is to combine this haptic estimation with MPC, with model predictive control. This work is done by my colleague Charlie Kemp at Georgia Tech. They use a model-based approach and then combine with the haptics to do this, MPC style control. Unfortunately, we can't really use a model-based approach because, simulating the dynamics for dressing in real time is just not feasible. So instead, we want to learn an MPC controller using the simulated haptic data in a model-free fashion. Again, we are going to reuse this simulated data, this simulated haptic data we generated for learning the haptic estimators. But this time, we're going to code the information slightly differently. The input of our training data will be the state history, the action, the candidate action, and the predicted measurement. And with that, we can create as many data as we need to train this LSTM to predict the future states. And finally, we're going to combine this predictor with the estimator so that now the predictor will take the history of the states, take one candidate action, and will give you a sequence of predicted states, and that will be fed into this estimators, which will give you the final the human haptic perception. And then we can define an objective function which prioritize the action that minimize the future haptic perception. Okay? So the one good thing about this method is that we decouple the objective function from the model training. So later on, if you need a different objective function for different tasks, you can do so without retraining our models. So we demonstrate our approach on a real robotic system that assisted 10 human participants in pulling a hospital gown onto the right arm. And with our haptic MPC controller, the robot can successfully dress the full arms in 98% of the trials that we did. This is the case. This is a failure case. That 2% failure cases we have. And we further compare suggesting results for various time horizon in MPC. And as we predicted, when you have a very short horizon like 0.01, the robot is not able to negotiate around the fist. And as we increase the time horizon, the success rate also increases. So what's next? We're actually the beginning of the third year of this 4-year grant, and we have touched each of those boxes, but we haven't quite pulled everything together into one system yet. So that's one thing we're going to do. Another thing we want to be able to do is to test this on a more unstructured scenarios. What can possibly go wrong if if a robot tries to dress a 4-year-old boy?
Make sure you have that run stop, Karen. Please watch Connor carefully. And Connor, if you don't like anything, just let us know. No, yeah, that's the one. No, don't. You're going to confuse the robot.
Yep. So we still have a long way to go. So with that, I'd like to thank my funding agencies and the institute that support my research, as well as my collaborators. And thank you for listening.
So we have time for a few questions.
Jim?
So I was thinking, looking at some of your the robot dressing results, do you have any intuition about how you might change the way a hospital gown is constructed to make robotic dressing easier?
Yeah, definitely. That's something that we didn't really need to come up with new thing, because there are existing modifications of a hospital gown to dress the patients with different conditions. So one thing is that you can. Well, the hospital gown actually is pretty easy to dress because it's super loose, and you dress in a different direction, right? You dress from the front, and then one thing they can do is, instead of making a knot in the back, they can make a Velcro. So they, there are other ways you can simplify that. But I think a more interesting question is like the more, ordinary attire like those that we're wearing here. How do you make them easy to dress, but still keep the aesthetics? And I think that's a separate problem from what I'm trying to solve.
Could you just use cloth that people could just punch through, so that you don't have to have sleeves? You just kind of put the tube on them and they punch their way out?
Yeah. I don't know if it's going to affect aesthetics. I'm guessing it will.
So can you talk a bit more about, right now, from what I saw, that robots, the person just kind of leave your hand up and the robots are just going to do it?
Right.
Isn't it more realistic, like the person actually move their hands and help the robot?
Yes.
How do you expand it on it?
Yeah, that's a great question, and that's sort of what I mean, that we want to integrate everything together, because we do have some kind of a human modeling that knows how to, collaborate with robots. And that hasn't been integrated into our robot controller yet, and that's our next step.
So in the videos, you'll see the robot sort of shake the
Mhm.
claw to move it. That is actually like a solution for peg and hold. And I was wondering, does the robot choose that kind of frequency to shake, or is there a limitation somewhere that?
Yeah, so definitely not choosing the frequency. That's sort of it's just emergent behavior. The robot is trying to follow a trajectories. The trajectory might go up and down a little bit, and the robot, I think there's like the combination of following trajectory and there's also some artifacts, which actually benefits in some is beneficial in some scenario, right? Because sometimes you just want to shake it loose a little bit, and then you can keep going. Yeah.
I think when we want to develop some human-robot interaction controllers, I think the one important condition is it must always do some expectable motions. In that sense, actually, I don't want to use deep learning because it's totally black box.
Yeah,
Is
yeah.
there any way you can make it more predictable to human?
That's a tough one. So it doesn't need to be a deep reinforcement learning problem. So yes, on the human side, I believe that the deep learning is probably the best way to go. But on the robot side, I don't know if you remember that the breakdown of the two problems. When you solve the robot control, it's just a simple value function, and you can parameterize robots in control in any way you want. So it doesn't need to be a neural network. In fact, the way we solve it currently is it is a neural network, but remember the control part is not, that neural network is replacing the simulation. It's not replacing the control. So the control part is still very, I guess, visible to human. You know exactly which control you're choosing.
I'll ask another question. So at the beginning of your talk, you showed this work with online system ID to do universal policy. Have you thought about applying that to the human case where you have different types of people, different human preferences, and you do online identification of that, something along those lines?
Yeah, I have not thought about applying to the different, like human preferences, but that kind of a learning can be applied to like multitask learning, for example. Instead of a model parameters, you can think about that as like a task parameters, right? Like instead of a, it could be like a parameterized space of a task. So that we have touched a little bit, but I think doing the human preferences is another possibility. You can identify that online and then apply to this universal policy to execute the best action.
Seems like that task could benefit perhaps by verbal communication between the robot and the person.
That would make it too easy or too hard. I'm not sure which one. But yeah, definitely that there are a lot of other modalities in terms of communication we can exploit. Verbal. So that's one thing. I think one of the ideas that my collaborator had us to sort of using a remote controller or like a gamepad to control the robots. You use that for one hand and the other hand trying to dress. That's another way. So yeah, there are definitely other ways to communicate between robots and the humans.
We should probably take other questions at the post-seminar reception. So let's thank Karen again.
Thank you.
So,
Close.
oh yeah,
I
right.
need to turn this.